The flap of a butterfly's wings in Brazil can set off a tornado in Texas. Of course, this may sound like a kind of joke or something, but trust me, it's way more serious than you think. You see, the world we live in operates in two fundamental ways, which shape the fabric of reality: the probabilistic mode and the deterministic mode. In the probabilistic mode, our universe unfolds with an element of chance. Small, seemingly insignificant events, like the butterfly's wings, can cascade into significant, unpredictable consequences. On the flip side, we have the deterministic mode, a world governed by rules and predictability. Here, cause and effect are tightly linked, and outcomes can be traced back to specific, identifiable factors. It's a structured reality where, theoretically, if we knew all the initial conditions precisely, we could predict the future with certainty. So, how do these modes coexist? Can the flutter of a butterfly truly influence something as powerful as a tornado? How much of our world is governed by chance and how much by rules? Answering these questions might seem beyond the scope of science, but things are changing. This puzzle is central to chaos theory, a tool that helps us see the surprising connection between things that appear disorderly and those that are highly organized. Here's how the story goes. Imagine playing a game called the Chaos Game. All you need is a blank sheet of paper, something to write with, and a die. Here's how it works. Start by marking 3 dots on the paper, like the vertices of a triangle. Let's call them A, B, and C. Also, mark another point within the 3 marked dots as your starting point. Roll the die. If you get a 1 or 2, mark a dot between the starting point and A. If it's a 3 or 4, mark a dot between the starting point and B. For a 5 or 6, mark a dot between the starting point and C. For example, if you roll a 2, mark a dot between the starting point and A. Roll the die again. Let's say you get a 2 again. Now mark a dot between the last point you marked and A. Repeat this process. Keep rolling the die and marking dots accordingly. For example, if you roll a 4, draw a dot between the last marked point and B, and continue this process. After doing this for a while, you'll end up with seemingly random dots on the paper. But here's the interesting part. What if these seemingly chaotic dots lead to something unexpected? To see some results, we can ask a computer to do this. And when I tried one of them, the result was very shocking. In that, I set the number of points to be 3, clicked start, and set the speed to fast. The starting point, or referred to here as the trace point, started moving, marking points. After waiting for about a minute, this was what I noticed. Looks familiar, right? It is indeed the Sierpinski triangle. Random dots and chaos lead us to such an orderly and symmetrical pattern. This is a part of chaos theory, which is usually defined as the branch of mathematics that focuses on the behavior of dynamical systems that are highly sensitive to initial conditions. So, the initial conditions in this case were the 3 dots from where we began, and the rule by which we were marking the dots. If instead of 3, you begin with 5 dots, then you would get a different pattern. In chaos theory, apparent randomness leads to various patterns, fractals, symmetry, and many more. You can head over to the website to try it out yourself. The link would be at the description of this video. But don't go anywhere yet. For another example, we'll need to start with a random number, like this number on your screen. Now, in each step, we multiply it by 10 and remove the digit in front of the decimal point. Multiply by 10, you'll get this. Remove the digit in front, and you'll get this. Multiply by 10 again, this is what you'll get. Remove the digit in front again, you'll get this. This process seems deterministic because it follows a fixed rule. Now here's the catch. Can you predict the future of our number? The answer is both yes and no. Initially, you can predict the outcome accurately for a few steps. But after a certain point, the precision becomes crucial. Computers, for example, store a limited number of digits after the decimal point. After applying our formula around 15 times, in the case of a 64-bit double, the results become unpredictable. This unpredictability arises because our formula discards information with each step, specifically when removing the digit in front of the decimal point. Even if you started with more accurate initial conditions, like 100 or 1,000 digits after the decimal point, the results become unpredictable after a certain number of steps due to the critical dependence on the initial condition. This is a simple illustration of a deterministic system becoming chaotic and unpredictable over time. Chaos theory is about equations or systems that are deterministic. meaning that there are clear instructions on how to calculate the future from the current state without any random elements involved, but that at the same time depends so critically on the initial conditions that it is impossible to predict the long-term future. But how does any of this affect us? Chaos theory provides a scientifically quantifiable but simultaneously poetically suggestive way of looking at how almost everything in life is connected with everything else. Anything that has definition and coherence, such as a single-celled organism, a war, a novel, or a flock of birds, is a system. Anything that changes, grows, deepens, or expands is dynamic. Anything that depends upon subtle chains of cause and effect, such as a fender bender, leading to a conversation, leading to a date, leading to a marriage, leading to a family, is deterministic. Perhaps most importantly, any system that is open to rapid and unpredictable change, not moving in a straight and unbroken trajectory, is nonlinear. The most interesting, intriguing, challenging, and exciting things in life tend to be dynamic, deterministic, nonlinear systems. Chaos theory challenges the certainty of traditional science by acknowledging a fundamental truth that science has often hesitated to admit since the Enlightenment. We can't know all the answers. While chaos theory doesn't replace the Enlightenment's idea of scientific determinism, it emphasizes that even with an abundance of data and information, we can never be entirely certain about the behavior of any system. This uncertainty persists, especially when systems interact with others and are susceptible to the influence of small changes. Even seemingly simple systems, like a swinging pendulum or a child's house of cards, can quickly descend into disorder. What's surprising, however, is how highly disordered and chaotic systems reveal unexpected patterns of simplicity. Chaotic systems tend to follow specific, stable pathways over time as they navigate through their operational phase space. These pathways are influenced by attractors, with the strange attractor being a unique type found in nonlinear systems. It displays both long-term stability and short-term unpredictability when mapped out in its phase space. The title strange attractor refers to a specific kind of attractor, showing that chaos theory doesn't just lead to disorder, but also unveils hidden patterns within the complexity. When closely examined, the simple lines of these attractors reveal layers upon layers of intricate complexity. Patterns repeat themselves infinitely, a concept known as self-similarity across scale, seen in natural systems such as snowflakes, fern leaves, and mountain ranges, all explained by fractal geometry. Fractal objects possess unique properties, and one of the key concepts is a modern interpretation of what older scientific terminology referred to as microcosms and macrocosms. The term fractal was introduced by mathematician Benoit Mandelbrot and refers to the fraction that can exist between dimensions. In natural systems, like an alpine mountain range, the degree of jaggedness observed on a single mountaintop will remain consistent with the degree of jaggedness across the entire range, extending across the horizon. This concept of a consistent fractal dimension illustrates how irregularity is a characteristic property that persists across different scales in natural phenomena. This mathematical framework embraced the irregular, the jagged, and the ever-repeating patterns that Euclidean geometry had deemed unruly. With fractals, Mandelbrot could quantify the coastlines, model the intricate branching of trees, and even understand the turbulent flow of fluids. A fractal is a never-ending pattern that is self-similar across different scales. They are created by repeating a simple process over and over in an ongoing feedback loop. Driven by recursion, fractals are images of dynamic systems, the pictures of chaos. Fractals are the unique, irregular patterns left behind by the unpredictable movements of the chaotic world at work. Fractals depict chaotic behavior, yet if one looks closely enough, it is always possible to spot glimpses of self-similarity within a fractal. Fractal order is a unique and surprising byproduct of chaos. This is the difference between the chaotic and the simply random. Chaotic systems never repeat themselves while remaining an identifiable system, whereas random systems can fall into repetitive cycles because they are free to end back at a point where they once began. For example, 5 fish swimming in a tank is a chaotic system because all 5 will never be in exactly the same position with the same direction and momentum twice. Rolling 5 dice is random because it is perfectly possible to roll the exact same combination several times. Each chaotic system exists within the borders of its own phase space, so if the system never exactly repeats itself, then a graph of the system's movement will necessarily have to have an infinite number of dots, with no two ever taking up exactly the same space. One would expect the dots to appear randomly on the paper, and for a while they do. Sensitivity to the butterfly effect makes a dynamic system open to radical change, usually as rapid as it is transformative. A favorite example of complexity theorists is the sand pile. One grain of sand is unlikely to make a difference at any single moment in time, but sooner or later, one of those single grains of sand will inevitably trigger a collapsing landslide. These are called phase transitions, and chaos theorists have identified unexpected stabilities in the ways one state of matter exponentially bifurcates into another. Systems that are most receptive to phase transitions are those that live on the edge of chaos. At a fundamental level, the universe is quantum mechanical in nature, full of an inherent indeterminism and uncertainty. If you take a particle like an electron, you might think to ask questions like, where is this electron? How fast and in what direction is this electron moving? And if I look away right now and look back 1 second later, where will the electron be? They're all reasonable questions, and we'd expect that they'd all have definitive answers. What happens in the quantum world is quite strange and can be a bit unsettling, even for physicists who've dedicated their lives to studying it. Imagine you want to know exactly where an electron is. The odd thing is, the more precisely you try to figure out its location, the less you know about how fast and in which direction it's moving, its momentum. On the flip side, if you try to measure its momentum, you become less certain about its exact position. Here's the tricky part. To accurately predict where the electron will be in the future, you need both its momentum and position. However, due to this uncertainty principle in quantum mechanics, you can only predict a range of possibilities for its future position. So, to find out exactly where it is at some point in the future, you'll need to make another measurement at that specific time. It's a bit like trying to pin down both where and how fast a tiny particle is going, and the more you know about one, the less you know about the other. Quantum physics introduces fundamental uncertainty, but when dealing with larger everyday objects, Newtonian physics is usually more than enough. Unlike the unpredictable nature of quantum mechanics, Newtonian physics is entirely deterministic. According to Newton's laws of motion, especially the fundamental equation, force equals mass times acceleration. If you know the starting conditions of an object, like its position and momentum, you should theoretically be able to precisely predict its location and motion at any future time. The equation describes what happens in the next moment, and as time progresses, it continues to guide you about what will occur in each subsequent moment. As long as we're dealing with objects where quantum effects can be ignored, these rules of Newtonian physics work seamlessly, providing a clear understanding of how an object will evolve over time. Even with completely deterministic equations, there are limits to how accurately we can predict the behavior of a Newtonian system. This might be surprising, and you're not alone in feeling that way. Many prominent physicists, even those who extensively studied Newtonian systems, initially believed there would be no such limit. Back in 1814, mathematician Pierre Laplace expressed this perspective in his treatise titled A Philosophical Essay on Probabilities. He envisioned a scenario where, if we could gather enough information to determine the state of the entire universe at any given moment, we could use the laws of physics to predict absolutely everything about the future without any uncertainty. However, as we've come to understand, the actual limitations of predictability in complex systems, even in the realm of Newtonian physics, have proven more nuanced than initially imagined. The necessity of introducing probabilities into predictions about the future doesn't always arise due to our lack of knowledge about the universe or the peculiarities of quantum phenomena like Heisenberg's uncertainty principle. Instead, it can be attributed to a classical phenomenon known as chaos. Even if we have a precise understanding of the initial conditions of a system, deterministic equations such as Newton's laws of motion do not always result in a deterministic universe. This revelation dates back to the early 1960s when Edward Lorenz, a meteorology professor at MIT, sought to improve weather forecasting using a powerful mainframe computer. Despite having what he thought was a reliable weather model, a comprehensive set of measurable data, temperature, pressure, wind conditions, etc., and a computer with considerable computational power, Lorenz attempted to predict weather conditions far into the future. He formulated a set of equations, input the data, and ran the program. However, when he re-entered the same data and ran the program for an extended period, the results were not what he anticipated. This unexpected outcome marked the recognition of chaos in deterministic systems. Remarkably, during the second run of the program, Edward Lorenz observed a surprising divergence. A minute difference at one point quickly led to the two systems behaving as if they were entirely unrelated, evolving chaotically in relation to each other. Upon investigation, Lorenz discovered the root cause. When he re-entered the data for the second run, he used the rounded-off values from the computer's printout of the first run as input parameters. Though this discrepancy might have seemed insignificant, possibly corresponding to the width of an atom or less, it had a profound impact on the outcomes, especially when projecting the system far into the future. This phenomenon, where minuscule, imperceptible differences in initial conditions result in drastically different outcomes, is what we know as the butterfly effect. It illustrates that even in entirely deterministic systems, chaos can emerge from the tiniest variations in the starting conditions. Because we can never know all the initial conditions of a complex system in sufficient detail, we cannot hope to predict its ultimate fate. Even slight errors in measuring the state of a system will be amplified dramatically, rendering any prediction useless. Since it is impossible to measure the effects of all the butterflies in the world, accurate long-range weather prediction will always remain impossible. While most traditional science deals with supposedly predictable phenomena like gravity, electricity, or chemical reactions, chaos theory deals with nonlinear things that are effectively impossible to predict or control, like turbulence, weather, the stock market, our brain states, and so on. These phenomena are often described by fractal mathematics, which captures the infinite complexity of nature. Many natural objects exhibit fractal properties, including landscapes, clouds, trees, organs, rivers, and many of the systems in which we live exhibit complex, chaotic behavior. Recognizing the chaotic fractal nature of our world can give us new insight, power, and wisdom. For example, by understanding the complex, chaotic dynamics of the atmosphere, a balloon pilot can steer a balloon to a desired location. By understanding that our ecosystems, our social systems, and our economic systems are interconnected, we can hope to avoid actions that may end up being detrimental to our long-term well-being. The universe is vast and unpredictable. Chaos is not just in the weather, it's part of life, reflecting our existence. Our choices have far-reaching impacts, like the ripple effect of a butterfly's wings. Chaos often emerges in systems with something we call feedback. To explain this, you'll need to think of the stock market. When a stock's value goes up or down, people react by buying or selling. This action, in turn, influences the stock's price, creating a cycle of chaotic fluctuations. The continuous feedback loop in the stock market is a simple yet powerful example of how small actions can trigger larger, unpredictable consequences in complex systems. Another example of this is a predator-prey relationship in an ecosystem, such as wolves and deer. When the deer population is high, there's an abundant food supply for the wolves, causing the wolf population to increase. As the wolf population grows, they hunt more deer, leading to a decline in the deer population. Now, with fewer deer, the wolves have less food, causing their population to decrease. This creates a feedback loop. The abundance of prey influences the predator, and the abundance of predators influences the prey. This cycle continues, with the populations of both wolves and deer fluctuating over time. The feedback mechanism in this ecological system can result in dynamic, often unpredictable changes in population sizes. Any system where the actions of its components influence each other can exhibit feedback, leading to complex and sometimes chaotic behaviors. Feedback in chaos shows that perfect predictability is often an illusion. Accepting the inherent uncertainty can be liberating. Instead of trying to control everything, we learn to adapt and navigate the emergent patterns that arise from the constant interplay of feedback loops observed in the world. Simple things, chance encounters, spoken words, or quiet ideas, are like the wings of our lives. Embracing the unpredictability sparks creativity and turns us into improvisers, shaping not only our lives but the world around us. Chaos theory might be a spark for a new wave of thought, not just for scientists, but for everyone curious. The ripple effect prompts us to rethink chance, order, and our role in the bigger picture. The key takeaway of chaos is this: Even when your equations are perfectly deterministic, you cannot know the initial conditions of arbitrary sensitivities. When the present determines the future, but the approximate present does not approximately determine the future, is chaos. If we ever find a final theory, chaos theory's lessons will be a vital link. It reminds us that beneath life's complexity, there's simplicity waiting to be understood. Philosophers, scientists, and everyday people may then gather, not as strangers to the universe, but as explorers sharing the quest to understand why we are here. In chaos, we may not find all the answers, but we might discover the wonder that connects us to the universe and each other. Thanks for watching, and subscribe for more videos.